Or maybe you're already done. Anyway, happy Wednesday. I just wanted to know, can you guys at home hear me okay?
Yes.
Okay, perfect. Thank you. I just wanted to make sure my audio in my morning classes today was not very good. So I just wanted to make sure. So we are going to finish up chapter 13 today. Chapter 13, we're talking about carbonyl compounds, specifically aldehydes and ketones. We once we complete this chapter, we'll move on to another chapter that does have carbonyl compounds in them. But that's like a whole nother scope with like different reactivity. They don't react the same as these ones. So yeah, we'll do that. Just a quick reminder before I jump in and lose track of like what's going on, because that happens a lot. I get really excited about this stuff and stoked, and then I forget about things that I want to tell you. So I want to remind you that your problem set 3 is due today. It's due at like 11:30 p.m. or something like that. As long as I have it in the Dropbox by tomorrow morning when I wake up, we're good. In the morning when I wake up, I will turn off the Dropbox so that you will not be able to submit it. So just make sure that it's in the Dropbox. I wake up at like 4 or 5 in the morning. Well, I can't help it. I can't help it. So yeah, just make sure that it's in the Dropbox by then. Last night I fell asleep at 9:30. Oh, yeah. So typically it takes me a while to go to sleep because my son is always like, Mom, I need to go do this. Mom, I need to do this. And it's like an hour and a half routine. So I don't get into bed normally until like 9:30, unless I fall asleep on the couch, which happens a lot. But, no, I have way too much stuff to do in the next like 2 days. So I have a difficult time sleeping when I have a lot to do, which is silly. Yeah. Another thing I wanted to say is that our exam was moved, remember? So we were supposed to have an exam on Monday, which would be in 5 days. We no longer have an exam in 5 days. We moved it, so now your exam is 9 days away. So not in 2 days Friday, but the Friday following.
What chapters are
Say that again?
What chapters is the exam on?
Need to make this louder. Okay, hold on. Hadiel, is that you?
Yeah.
Okay, well, I'm sorry. What did you say? I apologize.
Oh, I was just asking what chapters the exam was on.
So we are probably, I want to see how far we get on Friday. So it's my motive for pushing back the exam is not to include more on the exam. That was not my intention. I have this idea of where we're going to stop because I teach this class, and so I kind of know the progression all the time. And so I'm pretty sure that we'll stop somewhere on Friday. Like, obviously we won't finish chapter 14. I'm sorry, I'm not doing a very good job at this. So it will stop somewhere at the beginning of chapter 14, which that is the next chapter that we're going to start, and we will likely start it today.
Okay, thank you.
I will put, how about this? I will put a topics list up. I'll put a topics list up within the next 24 hours.
Awesome, thank you.
Okay, you're welcome. Thank you. So then you guys have like exactly an idea of like where we're looking to stop, at least for exam number 2. Great question. Thank you. Okay. Yeah, I don't think, does anyone have any questions for me? No? Okay. All right, so I'm going to go back a slide. I want to start at the beginning. So we have talked about how to prepare aldehydes and ketones. We talked about what we could do with them, and those reactions essentially were just the reverse of each other. We can oxidize alcohols to become ketones or aldehydes depending on the nature of the alcohol, meaning like whether it's primary, secondary, etc. And then we can take those carbonyl compounds and add H2 across that double bond to make alcohols. And so that's what we talked about last time. We started talking about a new reaction, and this new reaction is the addition of a small molecule over a carbonyl compound. And so this reaction might look super scary. However, it does not have to be. We're doing the same thing. We have a multiple bond. So this multiple bond that we have, instead of it being, a carbon-carbon double bond, this double bond is a carbon-oxygen double bond. I'm hoping that you guys are relatively comfortable in terms of, hey, when we had alkenes, we can add this little baby molecule across this alkene and do whatever we want to it. That's kind of the same thing here. So we've got this carbon, we've got this oxygen, we've got this double bond. We also have a small molecule. Now, this small molecule is not like H2, because H2 would have identical sides to it, but it works the same way. And so what we discussed at the very end of class on Monday was that this reaction between either an aldehyde or a ketone and an alcohol in the presence of an acid catalyst makes this thing called a hemiacetal. What we said is that this reaction is quite similar to the alkene type reactions, where we are going to have disappearance of this double bond, and you can see I'm like crossing out the bond with green. I want to go ahead and break this bond too, and we get some new bonds that are formed, and that's between the oxygen, so this carbonyl oxygen, so the carbonyl oxygen of the carbonyl will always pair with the hydrogen of AB. And I'm using AB as that general scheme to suggest that we have a small molecule. So that's one thing that happens. And then if you remember, the other thing that happens is that the carbon is going to go with the OR part of the alcohol. Now, I can get into some crazy details of why this happens, It all comes down to electron density and electronegativity. And so what we have here, just in case if this helps you, if this doesn't help you, then don't listen. We know that oxygens are more electronegative than carbons. So if you have to pick the more electronegative part of this, that is your oxygen. The electronegative portion of this part of the molecule is going to hook up with the electropositive part of the other molecule. And that's because we know that in chemistry, opposites attract. So you've got a delta minus and a delta plus, and they like each other. The same can be said for this relationship down here. You've got OR, and that oxygen is going to be electronegative. The carbon of the carbonyl is electropositive, and so they are attracted to each other to form that new bond. And so what we call this species right here, this particular species, this is called a hemiacetal. A hemiacetal is probably any organic student's least favorite functional group. You could probably ask other organic students, and this is probably their least favorite reaction. And that's because there's a lot of stuff going on in this thing. So hemiacetals, as I mentioned on Monday, they don't persist. You can't, if I were to do this reaction to try to hope to isolate this when it's not very stable, when it's very, very reactive, I'm going to have a hard time. So just to make sure that we're all good here, a hemiacetal is going to have a carbon that is down to both an OH and an OR. And this OR, you can view this, if I were to say this part, this looks like an ether. And you've got an alcohol. And so essentially, what makes this an acetal is the presence of both the alcohol and the ether on the same carbon. You guys are going to see hemiacetals in biochem. So that's why we need to talk about this. So I know we did a lot of practice trying to put molecules together. We took various ketones and aldehydes with different alcohols at the very end of Monday. And you guys pretty much hit the nail on the head. We're going to do that again. But before we go there, I want to talk about what happens after this. And I alluded to this fact at the very end of class on Monday, that these hemiacetals, they're very reactive. They do not persist. And so actually, these hemiacetals undergo a reaction themselves with more alcohol. So if I take a look at this hemiacetal, this is only a small amount of the product that's made. These reactions are done in an ocean of alcohol. That's the solvent. And if you guys remember the definition of solvent versus solute, solvent is the thing that everything is dissolved in. It's in the greater amount. And so there's a whole bunch of this stuff. And that's why there's going to be a subsequent reaction. There's still acid hanging around. And so this hemiacetal undergoes a substitution reaction to replace this OH with an OR. So let me highlight what the differences are in this structure. This OH is no longer present. Instead, what happens is this OR group takes place of the OH. The OH that was circled in pink, that is eliminated as water. The formation of this compound is called an acetal. And what makes something an acetal is the presence of two OR groups on the same carbon. So this is the special part. I'm highlighting this carbon in pink. There are two OR groups. And just remember, we've got like a superscript 3 and a superscript 4. And those just signify that they can be different R groups. They probably aren't. Or, I mean, maybe you can get different R groups, but a lot of times they're going to be the same.
I have a question.
Yeah, please.
So the OH turns into water basically, but where does the second H come from?
That is second H comes from here.
Okay, so the only thing that goes to the acetal is the OR.
Yes.
Okay.
Yes. So the two parts of each of the molecules that are circled in pink that I drew a line to, this will make the water in the product. And so that's a really good point, because this production of water, if you add a lot of water to an acetal, you actually go in the opposite direction, which is indicative of these arrows. So these arrows here, these arrows right here, this means that it's a reversible reaction. So you can go this way if you have a lot of alcohol, but as soon as you add a lot of water, the reaction goes back this way and forms the corresponding carbonyl compound and alcohol. So during these reactions are really cool. They have this like kind of rad setup where you do the reaction and any of the water that is generated is removed from the reaction. It's like really intricate, like all of this really dope glassware. It's so cool. So yeah, these reactions are pretty nuts. It's really cool. Okay, so would you guys feel comfortable doing some practice? Okay. So what I'm going to do is I'm going to open up a whiteboard, because I would like to practice on the whiteboard before I advance my slide. And the reason why I want to do this is because this is kind of how you're going to see your exam set up when you have a question like this. What I'll have is a compound. Why is this sideways? Plus an alcohol with an acid. And what you'll see then is another like arrow that has acid and more solvent. And so this is how I have all of these problems set up on an exam. So what I'm looking for is I'm looking for you to first generate the hemiacetal. And then in the presence of that acid catalyst and more alcohol, I want you to then put the acetal. So the part of this that you will see on an exam is going to be everything except for the word hemiacetal and acetal. I'm telling you this now. This is how these problems are on the exam. without these words. So this word is not here, and this word is not here. But if you see a carbonyl compound plus an alcohol in the presence of acid with another arrow like this is what I'm looking for. So let's go ahead and draw the first product, which is going to be the hemiacetal. If I want to draw the hemiacetal, what would you say I should do?
So, I think like for me, I don't know about anybody else. Like for me, I'm confused because we've been doing like we've been actually drawing out the structure versus doing the line structure. So, what's the first compound? Does that matter?
Oh, the first compound is just a ketone. So, this has 1, 2, 3, 4 carbons. So we would call this 2-butanone, just in case if you care about the name. But if you want to convert this into like a structural formula, I'm fine with that. But I also want you to see it in this form as well.
Okay.
You want me to put the H with the O? Yeah, I like it. Okay, so what I guess I'm gonna do is I'm gonna draw everything that is in black in the original structure. So 1, 2, 3, 4. Let me go ahead and number those carbons. 1, 2, 3, 4. From carbon 2, you said you want me to say OH. What do you guys think? So far, so good? Okay. All right. So yeah, we need an OH on carbon 2. What else do we need? Okay, we need the OR. And so this, would you say that this part is the OR? Okay, good. Because that's right. So O, and then what is the R group? CH3, right? That's it. So this looks funny how it's drawn, just because it looks weird to me. But yes, this is the correct hemiacetal. And what we know about hemiacetals is that they do not persist. They don't hang around. And so something else happens. How would you like me to draw the next thing that happens? Yes. So you want me to redraw all of this except for the OH? Okay. Yeah. Okay. Yeah. And then take the H. Cool. Can you put that next to it or like? you know, don't even worry about it. On a problem like this, just draw me the major product. This is perfect.
So we don't have to worry about the H2O.
Don't worry about the H2O.
Can you elaborate more how you got to the acetal?
So a hemiacetal, like this is very reactive. There is a whole bunch of this solvent left over. That's because this is the solvent, so therefore, like, there's probably, you know, thousands of equivalents of this solvent versus the hemiacetal. And so since the hemiacetal is very, very reactive, specifically this part right here. So the nature of this compound, this OH goes away, and in place of it is an OCH3. Because
Okay.
it's this part of the molecule. Shall we do another one?
Yes.
Okay. So you guys have time to kind of work through this in your head? So what should the first product look like? Okay, so you want me to replicate what's in black, and then you don't want me to have a double bond. You want me to have a single bond to an O? Okay. And then add the H onto it.
And then it's the O, just the thing that comes off the by itself.
Where? On the carbon?
The line that you're like drawing right now.
Oh, yeah.
Is that where the O goes?
Okay. And then?
Is that where it's at? Then we go to the next one. Or is that-
Yeah, we still need to complete this part, because like, check it out. You've got an O here, but there's nothing else attached to it. If you take a look at this one,
So we like put the little,
yeah, so here I drew the alcohol differently, right? I'm trying to change things up little by little, so you see how I'm not drawing the alcohol with the H up top and the O and the R down on the bottom, and now I'm switching up to fully line angle. But yeah, like this is a carbon, this is another carbon, like this alcohol is ethanol, right? So we can't forget about the carbonaceous part,
I feel
essentially.
like I forget that part of it, it's just a line.
I know, right?
Like it's just a line.
Well, so depending on what the alcohol is, you guys will see it differently. Like I tend to not, if it's methanol, for instance, I'll write the CH3. But it's really hard to look at methanol like this. Like this to me doesn't look like methanol. It looks like this is a substituent of some kind. So I think depending on the nature of the alcohol, okay, so what else do I need to do to the structure to make it correct?
Make it like go off the top.
Like that?
Another one.
Put another one. Okay. Wow, those are long bonds. I did it. Okay. Yeah. So this is great. This is our hemi-acetal for sure. Nice. All right. All right. Okay. Oh, go ahead. What's up?
I have a question. So, I mean, I thought of it as like you would put OCH3, CH2.
I definitely could do that, but if you look at that, you know, you've got an HH and then CH3 over here.
Mm-hmm.
So it would not be CH3CH2. This can't be it. But you could write OCH2CH3. This one is fine.
So it's the same thing essentially as writing than how you did the line structure.
Yes. This is equivalent to the line structure. I just decided not to write the atoms and I kept it in line angle. Okay, well, there's still some alcohol around, so what's going to happen?
Would you replace the OH with OCH3?
Well, this is our alcohol. How many carbons does this alcohol have on it? It has 2.
Yeah. I'll see what he wants.
So this is ethanol.
What?
It's not methanol. So depending on the alcohol, we can change up those R groups. So what is the R group going to be? You said you wanted me to change out the H for something. What is it going to be swapped with? Ethanol? Yeah. There we go. So this is your acetal for this reaction. Are you guys feeling it? Do we need to do one more? Yes? Okay.
Let me see it. Oh, where is it? Okay, it's over for you. Thank you.
All right, so you guys can see that we have lots of stuff going on, and it doesn't have to be scary. So which side is the carbonyl compound on? The left or the right? Is it a ketone or an aldehyde? Ketone, that's right. This is a ketone. Good. Let's go ahead and number carbons because that's important. You can see that we have a 5-carbon parent chain. If I had to number this, just because I would call this 2-methyl 3-pentanone. If 2-methyl 3-pentanone reacts with cyclohexanol in the presence of an acid, what can we make? So, how would you all like me to draw this honey acetal first product? What's up? Oh, I was asking, what should I draw here? What's the honey acetal going to look like? Is the backbone like the major part of the molecule? Is it going to be the ketone or is it going to be the alcohol? Good. So what I want to do here is I want to replicate the ketone. Except for what? That's right. That double bond with the O is not going to be there. Okay, so I have the major skeleton drawn. what is going to be different, or what should I add to this picture?
I know you're like putting the H with the O, and then I'm unsure how you would connect like the cycle.
Okay, that's fair. So we've got our H on, and this H, just in case if you guys are missing it, this is that H. So I'll color code this purple. I mean, it's probably not the H, but that's okay. We're going to say it is. So the H, the purple H goes on the oxygen, and then the rest of the molecule gets connected to that carbon, to this carbon, carbon number 3. So what is the first connection to the carbon? If I draw a bond from carbon 3 to the rest of the molecule, what is the first connection that's made? Good. The oxygen, and then you just draw the rest of it. So if you need to like walk through the molecule at all, like number it, just so that you make sure that you don't miss that carbon, you can definitely do that. So I know I picked a big, scary molecule, but it's only for you to see that it doesn't have to be scary. It's just a repetitive thing here. So if we have this hemiacetal, what we know about the hemiacetal is that it's not persistent, that it reacts with more alcohol in acidic conditions. So what would you like the hemiacetal, how does the hemiacetal change into the acetal?
Do you just connect the other cyclohexanol to the OH?
Heck yeah, dude. That's exactly what I do. I'm going to connect the other cyclohexanol to the other. I'm going to replace that H, and I'm just going to do that. Whoa, that thing looks weird. It kind of looks like a rabbit, doesn't it? That's funny. Oh, does it look like a mouse?
Yeah.
Cool. You guys got this. Remember, it's not that scary. It's not that scary. Do it stepwise. I will always ask you about the hemiacetal and the acetal on short answer stuff. And it will look just like how I presented it.
Oh, I have a question about this.
Yeah, what's up?
So, you know how like we were talking about how you can go from like oxidized to like less oxidized and then like even less than that. If we're like in the middle part, we want to see going. If like you're asking us to like oxidize it.
That is a great question. And if I want you to, then I'll make it like explicit.
Okay. Because one of the things the like problem set with the tutor, she was like, oh, we have to keep going. Keep going.
Okay, yeah, that's a great question. So I don't think everyone heard that. The question was, what happens if you have something like a primary alcohol? Let me draw for you. So if we have something like a primary alcohol, like this, so this is propanol. Imagine if this were to undergo oxidation conditions. I mentioned that this can undergo oxidation and produce an aldehyde. But aldehydes, I mentioned, can undergo further oxidation to generate something that's even more oxidized called a carboxylic acid. So we haven't lost any carbons. The number of carbons is the same. The question was, if we're being asked to oxidize something like a primary alcohol, how do I know if I need to stop? Oh, this is a really bad stop sign. Do I stop here? Or do I go all the way to the carboxylic acid? And I said that I'll be explicit, but if I do ask this on a free response question, honestly, either one of these is acceptable. I hope you guys know by now that I'm pretty flexible. And if you state your case and it's fine, like there can be multiple answers, there can be different ways that you draw structures, I am down. I am okay. So either one of these answers would get full credit in my book unless otherwise specified. So great question.
I have a question.
Yes, please.
So for the carboxylic acid, this might be a stupid question, but why do you connect the OH to the double bond? Does that make sense?
Because that's the functional group. So that's where it goes.
Like, cause it's on the, so it's like on the double bond. Oh, okay. So, I mean, I guess I'm trying to imagine it like.
So it looks like, just imagine if I drew this in structural formula. This is what it would look like.
Okay, so the double bond to the O is kind of like, okay, I think I understand. I couldn't, with the line formula, it was a little confusing.
Okay, gotcha. Yeah, so this carbon, that's right here, this carbon's super happy. It has an octet of electrons. This is actually going to be a functional group that you guys talk a lot about in biochem. And that's because this is like one of the functional groups in amino acids. That's like the acid part of the word amino acid. It's for the carboxylic acid. So great question. And we'll start this chapter we'll start this chapter on Friday because I'm kind of going a little bit slow right now. So we'll talk a lot more about carboxylic acids. Great questions. Well, okay, let's go ahead and see what we have next. This is just the full sequence of starting with an aldehyde or ketone. So just remember that in the presence of acid, in a solution of alcohol, an aldehyde or ketone will first be transformed into a hemiacetal. And because there's alcohol all up in the mix, you're going to ultimately form an acetal. All right. Let's do this one. This is just another way of looking at things. you've got propanal. Prop means 3, propanal and methanol. What is the hemiacetal going to look like? We've been doing all ketone examples. So let's take a look at an aldehyde example. Okay, so I'm just gonna copy everything the same, and you want me to break the double bonds? And then what? Add the H? Good, perfect. Beautiful. So I'm gonna go ahead and redraw that down here. Because what we know is that hemiacetals do not persist and instead will react with another equivalent of methanol. And what is this structure? What is this acetal structure going to look like?
So instead of the OH, you put OCH3 or CH3O, however that's correct.
Yeah, it would be correct both ways, depending on how you write it. I like OCH3 when it goes that way. When it goes the other way, I like it the other way because it shows the directionality of everything and how it's connected. So that is perfect. Perfect, perfect. Nice. All right, you guys got this. So sometimes there can be molecules that are a little bit bigger. And maybe a molecule might have like a ketone or an aldehyde at one end and an alcohol at the other end. So instead of 2 molecules coming together, you might have 2 functionalities in one molecule coming together. And so that's what I want to spend the rest of our time on today. Oh, come on, really? Fine, we'll do another one. I thought my segue was so good. I misunderstood that I had another example. Do you guys want to do this?
Yes.
It is. It's like the same. Yeah. No, I'm glad you're seeing it. For sure. Okay, look, I got this part down. Okay, now what? What's gonna happen? What's gonna happen? H goes on the O. Woo! Yeah. There you go. So that's your hemiacetal, and it probably will look a lot better if I advance the slide because I didn't disable that thing. Great. So that looks a lot better, right? Okay, and then what happens from here? Yeah. Nice. Nice work. Nice work. Very good, very good.
I mean, I just so go into my brain and then that's something.
Good. Yes. Well, because there will be questions on this, right? And look, like there's two answers that go to this. So for sure. That's awesome. Okay. So here's where I thought we were going before I had one more example. Imagine you have a longer chain, and inside this long chain is both the carbonyl and the alcohol functionality. So what happens is that these two sides can come together as long as they get close to each other. So what happens ultimately is that when these come together, here's your carbonyl and here's your alcohol, it forms something called a cyclic hemiacetal. So it's a hemiacetal, but it's just cyclic. It's the same compound that reacted. So let's say I want to just get rid of all of this. And the reason why I want to get rid of all of this is because it's kind of daunting. Okay. I'm also going to get rid of this right now. And the reason why I want to do that is just I want to put an example of this right next to it so that you don't lose track. So what we're looking at, an aldehyde plus some ROH. And what we know is that the hold up. Here we go. So this is going to hang out together, and this H is going up here, right? So those are the new things. We've got a bond that's being broken, and two bonds that are forming. So you can see how when we bring these closer, this is good. So the oxygen is going to talk to the carbonyl carbon, and the hydrogen is going to hang out with the oxygen. And so we end up getting something that looks like this. And this is totally fine. You know, just if we need to, we can look at this carbon that I colored blue. That is your carbonyl carbon on carbon 1, carbonyl carbon. And that carbon is still right here, and that is what makes this a hemiacetal. So this is going to be a hemiacetal. And that's because it has the alcohol on one side and it has the ether on the other. So now what I'm going to do is I'm going to go ahead and erase all of the crazy blacked out stuff that I have here. It just so happens that this ketone or this aldehyde and the alcohol is in the same molecule. What I like to do is I like to number my carbons. This is absolutely pertinent. The carbonyl carbon will be carbon number 1, and then you'll number them accordingly. Coming off of carbon number 4, that is where we have the alcohol. Fast forward on over to this structure, When we combine these two, we have to recollect that oxygen is going to be part of the cyclic structure. Now, this can generally only happen if we form a 5-membered ring or a 6-membered ring. Anything else smaller than 5 or larger than 6 is likely not going to happen. This would be considered a 5-membered ring. So this compound here is a 5-membered ring. And the reason why is because if we start counting 1, 2, 3, 4, 5, there are 5 atoms in this ring structure. Oh my gosh. Sorry, I numbered my carbons wrong. Ah! So we've got 1, 2, 3, 4, 5, 6, 7. Okay, so here's a compound. In the presence of acid, what is going to happen? Well, we have a carbonyl compound, carbonyl part, and we have an alcohol. As long as either a 5 or 6-membered ring can form, it will. So do you guys see anything? Yeah, it sure is. It's so Sammy's here with hands, and Sammy said it's gonna come like this, and that's exactly right. So what we need to do, and what I like to do is kind of bring these things close together. So if I wanted to, and I don't know how you guys want to do this or how you want to visualize it, but I'm going to put carbon 2 here. So carbon 2, 3, 4, 5, 6. I've got an oxygen. Okay, so bear with me while I renumber. 1, 2, 3, 4. How did I miss a carbon? 1, 2, 3, 4. 5. I know I did. Okay, how about something like this instead? 1, 2, 3, 4, 5, 6, 7. There we go. So do you guys see like a ring that can be made?
So you just like bent it?
Yeah. This thing's probably pretty floppy, so it can do that. So essentially, like the new bonds that we're going to form are going to be this blue one right here, and this H is going to go up to here, right? And we're going to cut this up. That's what's going to happen. So let me redraw everything. So we've got this oxygen that is going to be connected to carbon number 2. So this is carbon 2. Carbon 2 is this guy right here. Carbon 2, 3, 4, 5, 6. And what's really important is that we follow the molecule. If you look at carbon 2, what else is attached to carbon number 2 that I don't have drawn here? Carbon number 1, right? I need to put carbon number 1 in there. Is there another carbon that's missing? Yeah, carbon number 7, perfect. Carbon number 7. Great. So this can happen. You can cyclize a compound that has a carbonyl and an alcohol in there. You just have to bend this thing, make sure that you figure out what the cyclic part is. I will be straight up honest with you. Only one problem of this will be on the exam. Only one. And it will not be too many points. Okay? And the reason why is, I mean, like, you might be like, oh my gosh, Dr. Larson, why in the heck do we have to do this? This is insane. I know. And that's probably going to be the most difficult part of biochem for you, starting out. Because in biochem, what you guys will be doing is cyclizing sugars. Now, I'm not going to go over this because this is covered in your biochem class. In your first chapter, right when you get in there, you're going to be told that sugars, which are a carbohydrate, they do not exist in a linear form. Instead, these sugars want to automatically cyclize. And so that's why if you ever see pictures of like something like glucose, which is a simple sugar, you always see it cyclize. And that's because it automatically does this cyclization reaction because of this red carbonyl and this red OH coming off of carbon 4. It allows you to form a really nice cyclic structure. So this is something you guys will go over. Another thing that you guys will go over in biochem is how sugars combine. And this combining of sugars, so something like galactose and glucose, these things, one of these, at least this galactose right here, this is a hemiacetal. Carbon number 1 is the hemiacetal carbon where it has an OH going up and then an OR going to the side. So this is a hemiacetal. And sugars combine to make more complex sugars, more complex carbohydrates. What makes something a complex carbohydrate is that there are multiple sugar residues or carbohydrate residues connected together. And so now, like, we form this thing called a glycosidic bond, and this is, right, this carbon 1 is now an acetal. So this is an acetal. This is your acetal carbon. Carbon number 1 is an acetal because it goes to OR. Up here is OR. So that carbon is an acetal. If we go to the other side of this sugar, this carbon number 1 is now a hemiacetal. OR and then OH. And it can be combined with another one, and you can keep going and make a big, giant, complex carbohydrate. So I just wanted you guys to be well versed in hemiacetals and acetals, because this is something that you will be using in your subsequent course if you're taking 1109. And just to finish out this chapter, the only thing that I'm going to ask you about keto enol tautomers is which one is keto and which one is enol. Keto looks like a ketone, so keto form has a C double bond O. The enol form is simply a constitutional isomer, and it's an ene, has an alkene, and then an OH ol. So this is called an enol. The enol is less stable. The keto is more stable. The only thing I want you to know from here is for you to be able to recognize a keto form and an enol form if you're asked to, and which one is more stable. And that is it. Okay? And then you guys can check out the end of the chapter for your summary of reactions and stuff like that. So please enjoy the rest of your Wednesday. Don't forget to turn in that problem set. Have it in the Dropbox before 6 a.m. Let's just call it 6 a.m. Because I'll be honest, I'm going to work out in the morning. I'm not going to look at my email until after 6 a.m. So get that stuff in the Dropbox by 6 a.m. Illinois time, please. And I will see you Friday.